So good afternoon. So let's start our afternoon session with the talk by Professor Cameron Tropea. So he's a retired professor of fluid mechanics and aerodynamics at the Technical Institute Amsterdam, Germany. He received his PhD in 1982 from the Institute for Hydromechanics, Karlsruhe, University, Germany. His research interest includes optical measurement techniques in fluid mechanics, interfacial transport and wetting phenomena, atomization, spray processes, and unsteady aerodynamics. He has been a member of the German Council of Science and Humanities in the period 2016 to 22. Since 2003, he has been the editor-in-chief of the Springer Nature journal Experiments in Fluids. He has an excellent publication record and his works have been cited in more than 7,000 publications. He is also the Henry Chair Professor of Department of Mechanical Engineering, IIT Madras.
Okay, so thank you very much and welcome everybody back from lunch. I have that terrible honor of trying to keep you awake after lunch early in the afternoon, but I also have to stay awake. So, and I'd like to start. You see some other names here other than my own. That's of course a thank you. And now I have to figure out how this works. And that doesn't work, but maybe if I have to touch that and then it works. Okay. And these are some of the PhD students who are now either doctoral or professors, and I have to probably include Marco also. He was once a PhD student. And on the lower part are some of our funding sources. So, and we're going to talk about spray cooling. And it's always good to have some expectations before you start, otherwise you'll be disappointed. And the expectations are the following. Spray cooling, of course, can be transient or it can be steady state. I'm going to talk about transient spray cooling because if you understand transient spray cooling, then steady state is a subset and is easy. Okay, so we'll talk about that. And the other thing I'd like to mention is that I'm not going to talk about thermal management systems. So if you're interested in that, then you can leave the room. But actually, I'm going to talk more about let's say basic physics and try and convey to you what's actually happening in spray cooling. So a little bit dampen your expectations in that sense. On the other hand, at this lower level of basic physics, it's a more general understanding and it's more universal for when you do go to this for different systems. And I'll be talking both phenomenologically and also analytically. So some of it's just some hand waving and you understand it, but I'll also have some equations, which I won't spend too much time on, but the cited literature is there. And I have a lot of slides, but the last 12 slides are literature. And so I'm not sure if these will be made available to you, but if you want it, of course, just tell me and I'll send you the PDF. Yeah, okay. So anyways, don't worry. I won't be showing you the literature, but it's all there. Okay. But in the end, I'd like to make you very optimistic about spray cooling. That we understand a lot now, and we're in a position, let's say, to move away from conventional empirical correlations and go to physics-based models. That's my main message, and that's what I'd like to convey to you today are these basic physics-based models. And this slide you've already seen at least once, maybe twice today, and it all simply says that spray cooling, in this case with water, gives you extremely high heat flux densities and higher than anything else. I didn't put on here also temperature. Now I have to figure out how this works. How do you get the pointer to work in this thing? Ah, okay. I think I have. I got it. Yeah, I understand. Yeah, I first have to get my cursor off to the other side. Then I have to turn on this guy. Okay. Good. I got it. Yep, thank you. Okay. So let's go. So we have several applications, and some you've heard about today, so chip cooling. Also quenching, so hot milled steel slabs and whatnot is then also spray cooled. And one which we did a lot of work in is forging, hot forging. So forging dies get hot and then you spray cool them in between individual castings. And so these are the type of applications, and they're all typically very high heat flux densities and usually high temperatures. So now I'm going to show you an experiment, not because I want to tell you about what we do in our lab, but this is an experiment that gives you the information required to understand the physics. And there's two parts to this experiment. I mean, if you spray cool something, you have to know everything about the spray, and you have to know everything about the slab. And so that's why we have two parts to this slide. The first is the spray characterization. You have to know all about the spray, not just how much goes into the nozzle at what pressure. That's uninteresting. What's interesting is how much gets on the substrate. How big are the droplets? How fast are they? And what angle do they go at? And what's the number density? Those are the four things you must know if you want to start looking at the physics. So this is the type of thing you have to have. You have to measure velocity and size of droplets. You have to measure also the number flux, with a patternator or something. And then, so that's for that particular nozzle. Okay, and then you have to know something about your slab. So you have to know, I mean, if you have a big slab and you've heated it up, and typically in the laboratory we make it adiabatic, so all the heat goes in one direction, so one-dimensional heat transfer problem. But you have to then know everywhere on the plate what the temperature or the heat flux is, not just integral, you have to know everywhere, because the number of droplets is different everywhere. Okay, so we do that, and then you have all the information to make physics-based models. So it's a lot of explanation, but I think you understand what's going on. And if you want to run the experiment, then you have to come. Now I have to do something that. Now I need the other thing here now. So just a minute. Sorry about that. I have to take this guy off and put him here. So this is the way the experiment runs. You heat up the slab until it's a certain temperature, uniform. And then once it's uniform, then you start the spray. And then you start monitoring where on the slab it's cooling down. Now you need the heat flux on the slab, and you do that with an inverse heat transfer problem. So you know the temperature, and you know the boundary conditions here, and so you just solve FEM, you solve the entire slab and find out what the heat flux is at the surface. That's the inverse problem. But then you know everything, and you know also everything about the spray. And then you need a fast camera that will, with a big Questar long-distance microscope, so you can see exactly what's happening on the slab. Because we have to know, I mean, is it a pool? Is it single droplets? What's happening? So if we want to make a model, we have to understand that. Okay, and this diagram here is a little bit funny. It's the typical, boiling diagram. So you see the temperature, and this is the heat flux. And now time is, so you start at some hot slab, and time runs here. It doesn't cool down much, and then the heat flux goes up tremendously, and it cools down, and then this is, of course, your critical. So I'm going to show that same, that's the boiling curve. I'm going to show the same curve now in another way, and this is now in time, you see? Here's the temperature is red. It doesn't cool down much, and suddenly it cools down a lot. And then if we look at the heat flux, it's almost not a very low heat flux, and then you get transition boiling. So this is film boiling, transition boiling, and nucleate boiling. Okay, so it's clear for the transient problem, we're going through different regions. We've called the film, transition, and nucleate boiling. And it's unlikely, somebody said it today, I think our first speaker said, it's a dream to get one model that'll do everything. It's not going to happen because the physics are different each time. And the camera will show us what exactly the physics are. So you can see not only that, so this is a typical boiling curve. Again, I showed in terms of temperature, these different thermodynamic regimes. And you can see already here, depending what temperature we start our slab at, the thing looks different. Okay, so that tells you immediately there's a memory effect. Somehow the system knows what went on before. The spray doesn't know that. Only the slab can know that. So it's very clear the slab and its thermodynamic properties, especially the effusivity, plays a tremendous role in spray cooling. And if you don't capture that correctly, you're not going to be able to continue the problem. And so that's a very simple deduction out of this picture. Okay, so again, now we start looking at the camera. What's happening in these different regimes? We have this regime here where really nothing happens. I mean, the temperature doesn't change much, and the heat flux is low, and we don't see any puddles or anything. This is above Leidenfrost, the film boiling. It's like at home in the kitchen on the hot stove, and the drop just bounces off and runs around. So there's a vapor layer there, and there's no heat, very little heat transfer. And then clearly, when we get into this region in transition and nucleate boiling, then we see puddles, and then we see evaporation. Okay, it's evaporation. We have the latent heat of evaporation using it. So now we have to say, basically, we wrote a book about the hydrodynamics of drop impact. We understood that. But now we have this thermodynamics. And the question is, does the thermodynamics change the hydrodynamics? And it does, of course. And that's what's new. That you have to capture in your models now. You have to capture how does the the thermodynamics change the hydrodynamics. And of course, out of that, you get the heat transfer. Okay, so now this is like a small tutorial, a four-part tutorial. We're going to look basically phenomenologically at these four sections: single-phase cooling, nucleate, transition, and film. And we can say, this is actually a film from Peter Stephan, this one. And, but the film I wanted to show for two reasons. One reason is it's a conjugate heat transfer problem. You have to capture the heat in the substrate. That's this part. You have to capture that, otherwise you don't know what's going on. And the other thing that I wanted to show you is that you have viscous boundary layers and you have thermal boundary layers. So this is, the blue is fluid and the red is substrate. And you have a viscous boundary layer, you have a thermal boundary layer, and then you also have a thermal boundary layer in the wall. So if we're going to now move from phenomenological to analytic, we have to describe these boundary layers. And these are diffusion boundary layers, so it's square root T. It's always square root T. It's all diffusion. And so we can write these out, and this will be part of our analytic solutions. Okay, so let's look. Here's convection. There's a drop coming down. It sort of spreads out and just relaxes. And with time, it will evaporate because underneath is hot and above is not so hot, and it evaporates. Takes a long time. Heat flux is low. Then we have nucleate boiling. So it goes, and it's so hot that it starts to boil, and bubbles come. And these bubbles, they go up, so and then they burst, and you get little droplets coming off. But notice one thing I will show you later. The footprint stays constant. Take a look. It's about the same area. So if we're going to have to do something about heat flux is, per area, so the area stays roughly constant. We're going to make that assumption. Okay, now we'll go to transition boiling. And now what happens is you get contact, you get immediately boiling, all these little droplets bursting, or bubbles bursting, and then the whole thing lifts off because you get a vapor layer then. And so that's the trend. That only takes a short time in the spray cooling when you're cooling down. And here's what happens in your kitchen. You have a vapor layer. It never makes contact, the liquid, with the droplet. Okay. And you can make some regime on nomogram and show at what temperatures and velocities these things happen. And I think people make entire careers out of making these nomograms. So, but this is typical. You can classify then what happens. So this is the contents of my lecture. Realizing I've already used 15 minutes, I have three sections: film, transition, and nucleate. So let's start with the film boiling. Remember, that's in time we went film boiling, transition, nucleate. In temperature, of course, it goes the other way. But let's take a look at the film boiling. So we have the situation that these things, they have a vapor layer and they just bounce off. So do they take any heat away? Let's take a look at how much heat they take away in that case. And you can't avoid this. If you're cooling down from high temperatures, it's not efficient, but you can't avoid it. And so let's take a look. I mean, you get a vapor layer that is some hundreds of nanometers, and the droplet is some millimeters. So it's basically, it's a 1D problem. You don't worry about the end effects. I mean, that's a million times larger than that. So it's a 1D problem, and so we make it into I just do it this way. We make it into this solid, vapor, and liquid film. And now we just simply look at the boundary conditions and solve the differential equations. They're all ODEs, one-dimensional heat transfer. Okay, so we have some boundary conditions at the solid-vapor interface. We have the contact temperature. We have the saturation temperature at the vapor liquid interface because it's evaporating. And then we know the heat flux through here plus your latent heat of vaporization. And this is, of course, the change of height of your vapor layer. So this is actually this could be, heat transfer 101 in undergraduate class. And so then we look and say, okay, if we do that at different Reynolds numbers, this is now my experiment I explained to you, we see that actually if you non-dimensionalize here the contact time, so the time it takes to go away from the surface, it's not Reynolds number dependent. What that means, it doesn't matter what velocity you go at, non-dimensionally it's all the same. You get the same contact time. Okay, so the non-dimensional contact, dimensionless contact time. Okay, so you go ahead and you have these thermal boundary layers, and you do your and here's the effusivity of your substrate of the wall, and you have to put that in because that determines how much heat can come out of the wall, how fast. That's exactly what effusivity is, and that's a material property. You don't have to measure that. You know that. Okay, and so you've got this in the solid, you've got in the liquid, and you basically have 3 ODEs, and you solve them numerically, and you get your solution. So we can actually solve for every single droplet that comes down. It spends, U divided by D time there, or no, D divided by U time, and it comes back up. And we actually only take the time it's spreading out, because when it's spreading out, the temperature difference is the highest, and the vapor layer is the lowest. And when it comes back again, it doesn't take much heat. Okay, so we can actually compute now the vapor layer thickness and the heat flux as a function of time. And this is in milliseconds, and so the heat taken away from a single droplet is the time it takes to retract. And here's the area squared and the heat flux and pi, and then you integrate it. And you can do that. We have the solution. So you get a solution. There's the solution. And the chi, that's the only adjustable constant. That accounts for the fact that there are some end effects out there that we didn't take care. It's basically 1. It should be a little bit, basically 1. Okay, so this tells you for every drop that goes down, you know how much heat comes out. So then if you knew now the number flux, the size of the droplets, and the velocity, you're finished. Because it goes so fast, it's just superposition. You saw the film. I showed you the film. And then if you want an H, that's per area per time. Then you have to say, okay, I have to now say how much of the area have I used out of the total area with the number of droplets. If you only put 1 droplet on a big area, you're only using that much of the total area. You have to scale your H. Okay, but you can get an H out of this. Okay, and then this is basically just saying you can do superposition in this case. Okay, so that's the and then you might say, well, but if I had not just a sparse spray but a very, very dense spray, they might interact with one another. It's true. There's a probability. If you take randomness, then it's a Poisson distribution. And I'll go a little bit faster over that, and you can, at higher densities, you can get some drop-drop interaction and make some account for that. But basically what I'm going to show here is those are different experiments from people. I think one was Germany and somewhere else, and you can see completely different size of droplets and velocities in the spray. We don't know how it was distributed in the spray. They just measured some means. And the dotted lines are our solution analytic. So I hope I've convinced you that we can go away from empirical correlations and do this analytically. That was above Leidenfrost. That was the film boiling. Let's go now to section 2, transition boiling. So just to repeat, it does make contact, and you get these bubble bursting, so you get a bunch of little droplets, but then these larger droplets go in basically to film boiling. So again, we can hope that superposition will be okay. The droplet doesn't stay long there, and when the next one comes, it's dry again. So we start again from where we were. And we can look at that situation. So we get lots of small droplets and then these larger filaments and ligaments that come up. And we call this the Marilyn Monroe effect. And the question is why? Because we want to now model this. And you can see how these things are coming up. Why would they come up and go away from the from the surface? Well, we have to look back to Marilyn Monroe. I actually learned just last month that was not filmed in New York because it was too noisy or something. There was too many other things going. They filmed it in Los Angeles, although it was supposed to be over a New York subway station. But anyways, I just learned that just as a side effect. Okay. Anyways, but it's clearly an updraft. And what have we got in this case with our droplet? You see, if we take a look at our droplet, this is from below, again, the large segments. But, oh, wait a minute. I've missed a slide. Yeah, okay. I'll come back to this slide. So what have we got? We have this hot substrate. We have this droplet. This is all droplet, but this is not blue. Why? Because it's heated up a little bit. So remember the surface tension. And if you increase the temperature, the surface tension goes down. That's why you wash your clothes in warm water. Okay, so that means the surface tension here is high, and the surface tension here is low. And that means it's pulling. So we have, it's pulling up. At the same time, we're creating a vapor here, and that's the updraft. That's the Marilyn Monroe updraft. So you can see what's happening. So now the question is, can we model that? And so I think I can go backwards because I skipped over a slide. I should probably. So this is what we're seeing from above. You can see the little droplets sometimes, and then the larger ligaments. And so this is now velocity and diameter. Normally, I don't like to use units in graphs, but let's just look at that for now. And then you can see here we have the rebound, and here we have the breakup and atomization, the transition. We call it thermal atomization. Well, I mean, it's pretty clear. There's a clear dividing line. This dividing line is d proportional to u squared, and the other is d proportional to u. And that already tells us d proportional to u squared, that's Weber number. Weber number is rho u d squared. Rho d u squared divided by sigma. So this is clearly a Weber number effect with surface tension. That's not. And that other one is not yet being described. We described it some years ago with new dimensionless numbers, and the other is Weber number. Okay, so we saw that already. So we have this contact time. How long does it take for the droplet to depart from the wall? This has been superseded. We have a new publication last year that shows the model now, the analytic model for this. But all I'm going to show you is that we're able now to predict very well our experiments in terms of contact time. So how long does it take for the drop to retract from the surface? And here again, a nomogram in these new numbers. When do you get transition boiling or transition? When do you get deposition? And when do you get atomization? Okay, and so this is a little bit out of this newer piece of work, 2023, where we basically say, can we also compute the heat removed by one droplet? And the answer is yes. And it's a little more difficult as the analytic part. I'll stay phenomenological here. But basically, it uses like a percolation theory. So how many bubbles have to appear before you get sort of a breakup of the total mass? Okay, and these are some additional remarks about that. Now I'm going to move to the nucleate boiling. And remember, I told you the footprint stayed the same because we need the area, no? Because we need Q is per area. And we're going to just assume that this thing comes down and spreads out to some maximum and then retracts a little bit and stays there. And we know that number. That's the hydrodynamic part. And so let's go and look and see if we can. That's from the side and from the top. Okay, so this is now with the infrared camera from below. And you notice at the edges you get completely different colors. This is temperature, and this is heat flux. And maybe I'll do that once again. This is a pet project of Peter Stephan, one of our thermodynamics professors in Darmstadt. Basically, it's saying in the nucleate boiling, a lot happens on the edges. And yeah, he uses the word microlayer, but yeah, I'm not so happy with that. But okay. Anyways, but you can see that it's on the and why? Why is it all happening on the edges? Well, because it's a very thin layer there. I mean, that's at the wetting front, and the heat is otherwise it's going into sensible heating of the bulk, and of course the deduction or the deduction conclusion that Peter Stephan makes is if you want to evaporate faster, make a longer contact line. And how do you make a longer contact line? Make it rough. Then you have a long contact line, and then you have a longer area that is thin and evaporates quickly. So, and it seems to work. Okay, so we wanted to compute, though, the heat flux from a single droplet, and these are just some stills from that last diagram. Okay, so let's take a look. This is now the measured contact time, all with that experimental rig I showed you. And this is the surface temperature, and this is, of course, the film boiling regime. That was the transition boiling, and here we are in the nucleate boiling. And depending on the temperature, we have different contact times, and you probably didn't recognize immediately, but it goes almost with -2 with the temperature. So I'll come back to that, because that's what we also get in the analytic solution, -2, and it agrees very well with this experimental solution. So here we are. Now that we're going to keep constant. Thermal boundary layer in the substrate is diffusion dominated. The heat flux density is this is your thermal conductivity, and then we have wetted area is some d0 squared. Okay, is proportional to, but we know the proportionality. That's the hydrodynamics, and then we'll just simply say, okay. What goes out is over the time it's there, that's the contact time until it's all evaporated, the heat flux times the area over the time integral, and that's going to be somehow related to. And now here comes the remarkable, completely non-intuitive result that if you say you have nucleate boiling, so a droplet goes down there and it bubbles away and evaporates, then you know how much heat was taken away, because it's exactly the mass times the latent heat of evaporation. And it doesn't matter how many drops you have, it all goes away. So you've got this very clear, basically an equality sign. Well, there's one factor missing, but it's basically the volume of the droplet times the latent heat of evaporation must be what you took away in that time. So it doesn't matter how fast it went down, it doesn't matter how big it was, you know how much heat was taken away, because everything evaporates. And so what we want to know is that. Okay, and why do we want to know that? Because that tells us the rate at which it was taken away. We know how much was taken away. We want the rate at which it was taken away. So we want to solve for Q dot. Okay, so here's the contact time. I've just, you can solve for that. And again, you have the effusivity of the wall, because if the wall doesn't supply you enough heat, it takes longer. So it has to deliver heat, and that's the effusivity. And so we make this all dimensionless, and then you get some solution, and it agrees well with everything in the literature. This is the contact time to scaled wall temperature, also at different pressures. So these are at different pressures, you get the same thing. And then you can look time averaged heat flux as a function of surface temperature, and sure enough, it's Reynolds number independent. Remember I showed you it was Reynolds number, contact time dimensionless was Reynolds number independent. And not only that, so yeah, okay. Let's continue then. So now I've got mixed up, I've pushed the wrong button twice, I think. Okay. So let's, we have these three sections. We have heat transfer rates for each of them, and still pushing the wrong button. And now what we want to do is go and say, in transient spray cooling, can we now compute sort of how much heat is taken away, how fast? So clearly you have to then take whatever substrate you have. It could be a flat plate, but it could be a cylinder or something more complex. And then you have to work out from this spray, what is the number of flux on this curved surface? And this is, I'm doing this with Nilo, and he's ready to quit, I think. But it's engineering. It's not science. It's engineering. But it's not simple. Okay, and then you have to do at every local area. You have to say, okay, I know my substrate temperature because I'm monitoring marching in time. And then I have to say what temperature has it. Is it in this region or in this region or in this region? And then I have to invoke the model which is appropriate and then solve it. And that's basically where we are now. Nobody's really done that up to now. That's what we're trying to do here in Madras or in Chennai. But let's look once again now at what's happening. So this is a film. You see the temperature of the substrate is this dashed line. And if we're patient enough, that will move. And this is the film boiling. You see, nothing stays there. It just bounces away. That's the superposition that we talked about. Now you see the temperature changed. And now we're in this region. So that was the Leidenfrost point, and we're now getting some first little bubbles and things staying there, you know, puddles, I mean, are staying there. But they're not interacting very much. I can tell you, you can have tremendously high mass flow rates in a nozzle. Let's say we were doing forging, we were doing like 25, 30 kilograms per minute. That's high. And there was almost no drop-drop interaction on the wall. I mean, if you start getting a pool, that's different. That's pool boiling. I mean, that's different. But if you're just staying with the spray boiling, and the key now, I think several people said that this morning, the key is now to monitor and adjust your spray so you always keep in the spray boiling region or the spray cooling region. So this is, and you can see the temperature is moving down, and you start getting now more and more, and eventually you're out of the spray and you're into pool boiling. Okay, so these are I tried to put them together here. But you can see we've tried to capture just these edges, you know, what is happening physically between here and here, and that's what you see in those fast movies. So the rest is actually for you not so interesting. We, you know, went there and did lots of experiments, and the red line is our theory, and the black lines are a lot of different experiments. You don't expect exact agreement in all cases, but it looks pretty good. And here in heat flux density, that was temperature, heat flux density. This is, sorry, I didn't tell you, this is non-dimensional time, so it's cooling down. Okay, and so we get basically rather good agreement in these different regimes. And so again, this is the nucleate boiling. All I said was there's some assumptions we make, and but if you do that, then you also get good agreement between theory and experiments. Okay, so we feel we have validated theories, and I repeat then, this is what we've done. Now we have to decide, as we're cooling down in time, we start up at the high temperature, and we say that's film boiling, and as it goes down, it goes into transition boiling, and then into nucleate boiling, and the question is when? I mean, is it a temperature-dependent thing, or is it a time-dependent thing? And we have to know when to switch our model in our code. And the most critical part is actually this Leidenfrost point, so this point of minimum heat transfer. We have to know when have we reached that point. I mean, we can do an experiment, of course, and we see it, but we want to be able to predict it, not do the experiment. And so how do we predict it? And we've actually made some progress on that. That's pretty clear. Going from the transition to the nucleate is not so difficult. We know the contact time for transition. We know the contact time for nucleate. And as soon as the contact time for transitional boiling reaches what we would normally get for nucleate boiling, we know it's now transitioned. It's okay. But the Leidenfrost point, that temperature is a little more difficult. And I'd like to convince you that this is different than what you would normally read in articles. Most articles will give you some empirical correlations and some temperature, but they're not of no use to you if you have a different system. But what we've done here is the following. The Leidenfrost, so we did this experiment, you see, and we could see the minimum point of Q. We measured it. And then we have dependence of that temperature on spray parameters. So for instance, we changed the mass flow rate in our nozzle. We changed the Weber number. We changed the diameter of the drops, the mean diameter. We changed the velocity of the drops hitting the substrate. This was, I forget what that was, Weber number something. But take a look. Depending on the substrate, whether it was steel or nickel, there was always a clear difference. And that goes back to that memory effect I was talking about. I mean, in the end, when it goes from this one physical of bouncing to little puddles, that depends on how much heat the substrate and how fast the substrate can deliver the heat to the liquid. So that's actually a material property of the substrate determines the Leidenfrost temperature. None of the spray parameters. And that's what was not recognized for a long time in literature. And we have actually a new, I think that one I told you about 23 is even, it gives you very exact expressions for what that Leidenfrost point is. Okay, so that closes the story actually. Now you can take some, if you know your substrate, and you have to compute, of course, FEM in the substrate, and you know your spray parameters, then you can compute basically how much heat you take out in one time. So I'm going to skip these few slides, and that's exactly what we're doing here at IIT Madras. Is now we're going to some, unusual. We're trying to cool down a cylindrical tube heat exchanger, and then we have to work out, okay, what are the spray parameters on some elemental area of the tube. We have to compute the tube, and then maybe we can think, we could have more than one spray and compute as we go. Some organic Rankine cycle system here in applied mechanics. Anyway, so that's the end of the story. I told you I'm not going to give you any thermal management system solutions. What I tried to tell you here was what is the physics behind the spray cooling, and that I think is where we are right now. We haven't really yet applied it to total systems. That's what we're trying to do. Thank you very much for your attention. Oh, I forgot to show you the 10 slides of literature. So in case you're interested, it's a good literature survey, so I think we can get it somehow distributed. Okay, but there's 10 slides. Well, there's quite a few slides of literature, yeah. Takes time to warm up. Yeah, we'll start here. Okay, and then this fellow in the green shirt. Maybe.
Greetings, sir.
Sir, I just want to know about the camera capacity, I mean FRPS, frames per second, FPS. What kind of camera you have used to capture such?
I don't know. We have probably 15 cameras, and we always have one camera too few. It doesn't matter how many cameras you have, you don't have enough. But yeah, I don't know. These are probably 25,000 a second, or maybe 50,000 a second. We have some that go to like 1 million per second, but they're smaller. But I don't think these are ultra fast. These are not really. But let me say, more interesting than, I mean, you can get cameras that go that fast, but more interesting is, of course, the long-distance microscope with a large numerical aperture, because then you get, better light intensities.
Okay.
Yeah, and you might have noticed in the films that we weren't using full aperture, so we had a rather large depth of field. Well, actually, we didn't have that large depth of field. No, I wanted to say that the other way. We had a large aperture and had a small depth of field, so if you went a little behind, they were out of focus, or a little before out of focus. Only in the middle we were in focus. That's because of the large aperture. It's a Questar QM100, or LM100, I think. Yeah, but we were using the fast cams also. We have all kinds, Shimatsus and fast cams and Phantom. I think he's got Phantom out here, no? Yeah. But let me say, it's a good question. That's not a limiting factor. Nowadays, you have enough cameras that are fast enough to do this. That's not. I mean, if you go into ballistics, it's something else. But for this kind of work, it's. I don't know if you have import restrictions still. No. Yeah. 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 So I think in green, if at the. Yeah. But we have 25,000 full frame now. I think the SX something, I don't know. Yeah. Your mistake is to ask the professor. You should ask the doctoral student. He'll know. I think in the green.
So we had a constant area assumption, right, sir?
A constant?
Area assumption during the film Boeing regime in the 1D case.
I don't know if I understand completely what you're asking, but let's say the different curves I was showing of Q and temperature in terms of time. So it's an excellent question. So we actually had a plate, so this big, but it was not integrated around the plate. It was integrated over like, a few millimeters in the middle. But we could have done it over here, over here, over here on that plate. Doesn't matter where we do it. We have the local number density, the local size, the local velocities, and the local heat flux. So you can do it everywhere. But I think most of what I showed was near the center of the spray.
I mean the area of the drops that hits the
area of the
drop that hits the surface. Yeah. Wetting area of the drop. Yes, sir. Because we
yeah. So we checked that. What you're asking is the uniformity of the spray. The spatial uniformity of the spray is what you want to know. And it's a full cone spray. And we measured, of course, the whole spray. Also measured that it was actually symmetric. And it doesn't really matter to us. Why? Because we measure where it is, and we measure the local heat flux and the local size and the local velocity, so we don't care.
So the local area or the local size of each drop is same all over?
No, it's not over the spray. It changes. In the middle, it's different than on the edge. Who cares? We measure it. But if you simulate, you have to know what your spray does. Of course. But let me say this is a paradigm change, because up to now, if you read literature on spray cooling, they say, "Oh, I put 3 kilograms per minute through the nozzle." Who cares? That doesn't determine what happens at the surface. What happens at the surface is the velocity, the size, the angle, and the number flux. And if you don't know that, then you're back into empirical correlations, and who knows whether they'll work.
So what about the drop-drop interaction? Is it a wild assumption to just ignore it?
Yeah, that's also an excellent question. So I skipped over that. That takes a little longer. But those are Poisson statistics. So you assume that you have the droplets randomly distributed in space and time. Okay, and once you know that, everything else falls out. Because then you say, okay, what would be the area of all these number flux droplets in a certain time? And what would be the probability that two droplets are close in time and space that they would have a less than the sum area? And that's Poisson statistics, and it turns out that you can go to tremendously high number densities before you get interaction. And as I said, we were getting up 25, 30 kilograms per minute out of this little hot forging die spray. And we were doing Monte Carlo, but you can do it with Poisson statistics. And I didn't show that curve, but you can go to very high values and get almost zero interaction.
Even post-disengagement, there is no almost zero.
Yeah, but let me say, the proof of the pudding is we get good agreement with other experiments. It seems to work. Yeah.
Thank you.
Yeah. But I think over here was also some question. Yeah, okay. Yeah, okay. Yeah. And it's already 2:40. Thank you very much.